Hello and welcome to day 4 of the Advent of Code 2021. Today I want to change things up a bit. If you've seen any of the first 3 videos, there I coded essentially, well, not really live since I was recording obviously, but you saw me coding the puzzle up of that day, including all mistakes I made and whatnot. And I figured starting from day 4, I don't want to do that anymore since I figured it's quite lengthy to watch. And also the time for me to edit it every single day of December is quite a bit, since I also have a full-time job at the side. So from day 4 onward, I will only show you how I solved it, explaining what I did, and hopefully you can get something out of it still. Right, I will show step by step, so it's not going to be like here's the code and we're done, obviously, but I'd say let's get going. I'm also going to skip the reading since I presume you know roughly what the idea is, so I'm just going to explain what we're solving. So for this puzzle today, we have to play bingo. So how this works is the first row of our input is the numbers that are drawn out of a pot or something for the bingo. So this is, in this case, quite a short list. In the actual input, it's well, a very long list of numbers, comma separated. And then there's a new line and an empty line with nothing. And then any number of bingo boards that you can see are matrices, essentially, 5 by 5. So we have 5 columns and 5 rows, and that's one bingo board. And then how this works is we draw a number every time, or iteratively, and mark which of the boards had this number, just how actual bingo works, of course. You can see an example down here. We do this until one board won. When does one win in bingo? Exactly when you have one row or one column anywhere on the board that is all marked numbers. Diagonally is not counting. Luckily, that would have made it quite annoying to implement. But either one full row or one full column is marked, then you won. And finally, what we still do then is we take from the winning board, the first one that wins, that is, we take all the unmarked numbers at that point in the simulation, you could say, because essentially we're simulating a game of bingo with multiple participants. And we take all the numbers that were not marked on the winning board, sum them together, which you can see right here. This is 188 for the example right here. And then we multiply that sum with the last drawn number out of our list right here. And if we do this multiplication, we have our final output of the puzzle to put it in. You can see I solved it already, so let's look how I did that. So we obviously start by first getting our lines. Here one can do one nice trick. So whereas in the usual previous puzzles, I split just by a single \n, which I also had this extension function for, to split like multi-lines into a list of string. In this case, actually, it makes more sense to split by a double \n, because what will that do? If we look at our input, the only time we have 2 \n behind each other is whenever there is whenever there's a separation between either the numbers drawn and the first board, or also in between all of the other boards. That means this gives us a nice property such that the first element in here is the line with the inputs, and everything else are the boards. So what we could also do here is get that out there directly. What we do next is we need our numbers that we draw. For this, what I did is I get the first of the lines right here, and I split it by a comma, such that we have each of the separate elements, and then I convert all of them to integers. And the thing that makes, in my opinion, at least sense here, is to create an iterator out of this, such that then this is quite naturally how you would also draw this. So you can just always say, give me the next number, give me the next number, and then continue drawing them until you have found a winning board. At the very end, we want to throw an illegal state exception if no winning board was found, such that here in the middle now we can implement finding one. So if we ever reach this, we know that something didn't go quite right. Let's now convert the rest of the lines. So we have the first one right here into the boards, right? The rest are the boards. So what I did for that is write a method, parse boards, that I give everything but the first line. So if you say drop 1, the first one is dropped because we already used it here for the number drawer. And then let's look at how parse boards works. But for now, let's focus on what we create inside of here that we pass in the constructor of the bingo board. So you can see it is a list of int, which is just, well, the numbers right here. Each row is a nested list, and then all of them, all the columns essentially, yeah, are the outer lists, just as any other matrix would work. So it's a 2D array essentially. So what we do right here is we split by a new line, such that we get each of the rows. And then for each of the rows, which you can see we have right here, I can again split by a space character, which then will give us each of the elements in one row. We have to filter out everything that is not blank. That is blank, I'm sorry, since there are some like spaces in here that are extra. So this was formatted such that it lines nicely. So we have sometimes spaces that are not actually a number. So we have to filter these out, such that then we only have the numbers left and we can convert them to an integer, such that we have our list of int. That is, I think, pretty straightforward. And then finally, we pass whatever we received right here into our bingo board constructor. And in the end, then we have, of course, a collection of bingo boards right here from this whole expression. So let's now check out the bingo board. There's quite a lot of stuff going on, but let's start easy. So the first one we need to look at is, we have the bingo board, but what we also have is a cell. So this is a nested class within our bingo board. That is one cell, so one of these numbers right here. Why did I make an extra class for this? The reason is pretty easy, is such that we can have not only the value, but also save if this is already marked or not. So you can see this data class contains, well, just the number value, as well as a mutable boolean, so var, not a val, that represents if it's marked at the moment or not. What they represented here in the puzzle with it being like lit up. So if the number is drawn, we can say, okay, now it's marked. So default obviously is false because everything starts being unmarked. And then you have a single method that just changes is marked to true, such that we can call that later on all of the cells that were drawn out of our number drawer. And to initialize the class, then we do the following. We get the this grid, the matrix that we receive here. And for each row, we essentially flat map not really flat map, but well, we map twice essentially into a cell. So we just convert each of the integers into a cell. So we just wrap it, as you can see right here. And since this is default to false, we don't need to say here false, such that we just start with all of the cells and being initialized. Then we do one trick, which we'll look at in a second. So this line right here, we look at in a second because it's only interesting later on. What is interesting though, for now still, that's going to help us is also, this is one integral part I think that is quite nice about this solution, is that I create a map that maps the numbers to the cells. So what we just do is we flatten the whole board into just the cells, and then we associate each cell by its number value. So associate by, all that it does is it creates for you a map that maps whatever you give here in the lambda to the value. So we receive a map of int to cell, which obviously only works because the numbers are unique. If we would, this is given in the puzzle description, if we would have a number twice in here, somewhere in the same bingo board, this would obviously not work anymore because the keys, they would clash. We could do then group by, which would give us back a list of cells, as you can see right here. But since this is given that it's unique per number per board, this is perfect. So why do we need this? The reason is, you'll see in a second, we can then very easily check if in this board a number that was drawn is contained. So all we have to do is look up in this map right here, hey, give me the cell with the associating number, and if there is a value for that number that was drawn, we know that this board contains the number. What I did for that also is this is quite nice, fancy Kotlin, I guess. We also have a contains function on the board, and as you can see, it's an operator fun. So what that means is that it overrides the in keyword. So what we can then do is we can say if one in board, and it will give us back a boolean if it's there. All we do obviously is just check if our map right here contains the given value, because then we know for a fact that this board contains that number, and this can be quite helpful for drawing the numbers, or for checking if they exist. So what do we do next with this knowledge? So the next step, you probably guessed already, since we have our list iterator right here, is a while loop. So we can just say while we still have numbers to draw, we keep iterating, and we draw the next number out of our iterator, which is, as I said, pretty closely simulating how an actual drawing out of a pot would work. So we have a number drawn here, and automatically it moves forward due to the iterator, every iteration. Then what we can simply do is this single expression here, which helps us quite a lot. So what we do is all of our boards that we have here, after having constructed them, we can, on each of them, we can call mark number and pass in a number that was drawn. What is mark number though? Let's check that out. So here's the mark number method, and all it does is you give it a number that was drawn. First thing, of course, that it checks is if the number is contained in this board, and that's precisely where you can now see where we use the operator contains for. So we can use this in keyword of Kotlin and negate it to know, okay, this number is not contained in the board, at which point we return false. Why do we return false? We'll see in 1 second, or 1 moment rather. So what we can simply do now if we're getting past the if, we know, okay, the number is on the board, so we want to mark that it was drawn, right? So what we can simply do now is take advantage of this map. Since the map was originally created out of the board, these cells right here are just references to the actual board. Because in Java you have you do have references, pointers of sorts. So if we work on the JVM right here with Kotlin, and we associate this by all the cells that we already used here, the cells in here and the cells in here are just the same objects, right? So a nice thing we can just do now is if we say give me the cell of that number, so we just look up on our map what is that cell, and we mark it. So we call the mark method, which literally just flips this boolean that it's now marked. And this will also do the same, or well, we'll also mark the cell in our board being now marked, which is quite nice, because then we can do the following. We have this check if one function that does precisely what it says. So all we can now do after a number was marked, we obviously have to check, hey, is this board a winner now? Winning being is there one full column or one full row somewhere that has all marked numbers? So after drawing a number, we can check this. We should check this to then notify essentially what is this boolean. So if this is true, returned by marked number, then we know that this board is a winner, and if it's false, we know that it's not a winner, which is now precisely the reason why if the number is not even on the board, we can return false, because nothing changed from the previous marking. So definitely not a winner. To check if we won, this is actually quite easy now. We just take our board and we map over all of the rows first of all, and check if all of them have is marked. This all method, if you don't know it, all that it's doing is you give it a lambda that goes to a boolean, and this will only return true if all of the iterations, so to say, were true. So it's essentially a map operation that at the end checks that everything that was mapped into is a boolean of true, but it's a shorthand and it reads a lot nicer. So we just say, are all of the elements in this row is marked? So what this would give us back is a list of booleans for each row, but we only need a single one to win, right? So what we can then just do is this any function, and we again give it something to check on. In this case, it's already boolean, so we can just say it right here. So what this expression simply does is it checks that any of these of the rows, or if we have any row where all of the cells are marked already, right? And the nice property about this is that it can short circuit at various points. So the all obviously can short circuit in the moment that it saw one of these that is false. This will obviously, well, not obviously, but it's implemented in a way that it will short circuit, it will abort checking the others because there's no point. It's not possible anymore to get all of them being true. So that's quite nice. You only check what you actually have to check. So let's say in our input right here, let's say these first two are true and then this one is false. It would iterate over here, then see, oh, this is false. So it doesn't even have to check the other two anymore, right? Because it's impossible to still have all true. So it will only iterate over the first three and then short circuit. The same here. Well, not the same here actually, because it's not a lazy collection. So we first check all of them and then continue. We could do this here lazily. So we only check one row at a time, such that this can also short circuit. That we could do. So if here, for instance, we would do S sequence, then we would only map row by row and then call the any on it, such that the moment that we found one row that is matching, we don't have to check any of the others anymore. So this actually is quite a nice addition that we can also apply here. Right, what is happening though in the next thing here? So what we obviously checked with this is if we have a matching row. What we did not check yet is if we have a matching column. So we not only have to check, hey, is there any row that is fully marked, but also is there any column from top to bottom? The way this can be done pretty easily is by transposing what I also did in the previous day, your matrix, and then doing exactly the same. So what is transposing? You simply take, you flip around what were rows to be now columns and vice versa. So we essentially rotate this whole matrix on a 5x5. It is pretty easy. So now 8, 27, 21 and so are the columns, and this is now a row. So you just turn this by 90 degrees, so to say, on an example here where it's a square at least, such that you can then very easily iterate in this direction, but while still doing an iteration. So we do the exact same right here. So you can see this time it's a column, technically speaking, and we check the same again and put an or. Boolean or in between, such that this can also short circuit, meaning that if we already in this first check right here we found something that is a row where everything was marked, then we also, it's not gonna evaluate even the second part. So there's now 3 places where it can short circuit, which makes this fairly nice to check, even though we still have to do a lot of iteration. Like if the very last column in the entire board is the one that is winning, then of course you still iterate everything, so it's not perfect. There are ways to do it a bit nicer, but it's still pretty nice. We can short circuit here, here, and here, and the same obviously with these two. Right, so this would just return us now if we won or not, and then we just return this from here, such that in the place where we use this up here, we can group by this. So this would simply mean that we have now a map of Boolean to a list of bingo boards. So we only have true and false as the keys, and then all of the bingo boards in there that are, well, have won yet or not. So if we would execute this, let's quickly do that to see a bit what's going on there. We would now see that how this grouping looks. So we have our winner grouping, and you see we only have false at the moment, meaning that there's no winners yet, which makes sense because we only drew a single number. You cannot even win yet. But if we iterate further and further, you will see that at some point we will have one that is a winner. As a matter of fact, the next thing that we check is, does our grouping contain the key true, which meant that we found a winner. So let's go one row further right here. And you see if we go into this if statement, the grouping looks like this. So we have 99 that are not yet winners, and one of them is a winner. So we have this board right here is one that won, and I guess we can quickly have a look where this won. Not here, not here, not here as well. Okay, let's check the transposed. So this is what the rows. Now check the columns. Here we go. So the third column is a winner in this board. All of these numbers were drawn already. You can see all of them are marked as being marked. And now we can simply I simply do a check right here that our winner group, so the one that this list right here is only a single element, because otherwise we have two winners, which is not expected. So we check this right here with the require, which would throw an exception if it wouldn't, and then we just get the first one out of the group, which is then the winning one. And that's pretty much already the whole puzzle, because all that we have to do now, if we remember back to this, is get all the numbers that were not marked yet on this board and sum that together and multiply it by the last drawn number, which is precisely what happens here. We get all unmarked numbers, sum them together, and multiply it by the drawn number up here. Get all unmarked numbers is very straightforward. We can just flatten our board to get like literally all the numbers, filter out all the, well, all cells, technically speaking, right? This is the board is cells inside. Then we just filter out everything that is not yet marked and only grab the integers, such that here we can return all the non-marked integers. And if we run that, we get our result. Let's move on to part 2 then. So part 2 is pretty straightforward in today's puzzle. So all we have to do there is that we have to find out which board will win last and then do the same. So we instead of finding the first one that wins, we find the last one that has all one column or one row fully marked, and then we again take all the numbers that were not marked, sum them, and multiply with the last row number. Same algorithm. So this can be done quite easily by copy pasting large parts of this. I could have put this into methods, of course, like this part here, getting the iterator and so on, but I figured, I mean, it's a one-liner, doesn't make a lot of sense to put this into a whole bunch of methods. So there's only one small difference that I applied to do this, which is that now our boards right here are a mutable list. So you saw here it was just a collection, so not mutable. You cannot remove or add any boards after having constructed it. In this case, we make a mutable list with the whole idea that every board that won already, we remove from this list, such that we know once the list is empty or has only a single element left, that's the one that won at the very last. So all we do right here is still the same. We group by who won yet or not, and then if we have one that contains, if we have a winning board, we get all of the ones that won. So this is all the winning boards in this list right here, and then we say from our boards that are still in the race, we remove all of the winning ones. Let's quickly run that as well, how this would look like. So it makes a bit more sense what's going on there. So this would look like the following. We have our boards right here, and you already see we excluded one, obviously, because we went into this if statement here, so we must have had a winner. And then you can see here where it says size 99, this should like shrink over time. So you see we have more and more winners. Sometimes two may win at the same time. Most often probably it's just a single one. Yeah, there's a few more. So this list shrinks and shrinks and shrinks and shrinks and shrinks all the time, until one point where we can check if boards is empty. So once we remove the last one, since we remove here and immediately after check is it now empty, it's safe to assume that the one that is still in this group must have been the one that won last, which is precisely what we're doing here. So out of our previous winner group, we get the first one. So here we can be certain, once we reach this point, that this one must have been the last one that won. So you see now boards is entirely empty because we removed absolutely everything, but we also know that this one is the one that we removed the last time, since the check is immediately after removing things. And then we have our last board that won, and then we do literally exactly the same as we did the last time. So we can get all unmarked numbers of that board and do this calculation right here, and then that's done. One thing I want to mention at the end, that is quite important for this one, is that for this to work, it needs to have a valid equals method, the bingo board class, because otherwise, if you say remove all of these boards out of my other list, you either, well, you need hashcode and equals, in this case equals, such that the JVM can check, hey, the ones that you give me here, which are those in this other list, such that I can eliminate those. So the only thing that is important here is that this is not a data class, right? So it doesn't have hashcode and equals by default, that we override them. In this case, I just chose that the way to identify if two boards are equal is if the board 2D list here is equal, because we assume that we only have one board with all the numbers at the exact spots once. So of course, if we would in this input have two that are like exactly identical, that would not work. But then on paper, technically speaking, they are also the same board. So I guess this is fine. So that's just what this equals and hashcode here checks, such that we can use our remove all without any trouble. Right. That is all there is to say for day 4 of the Advent of Code. If you have any questions, if something was not clear, then please drop me a comment. I'm very happy to help you out a bit, respond to that. And yeah, please share your solutions that you wrote in Kotlin, or honestly any other language. I'd be very happy to see them, because it's very interesting how other people solve these ones, because obviously there's 100 million ways, specifically with this one that is a bit more difficult than the first 3 to solve it. Please also join my leaderboard. If you participate, you'll find the code to join in the description under this video, and then I'll see you tomorrow. Tschüss!